Welcome to the CFD-Post tutorial for Blue Sky Solar Racing at the University of Toronto. Alright, so this tutorial will go over how to import or set up the CFD-Post module, how to open CFD-Post, the mesh entities that will be present, and which ones you'll deal with, the coordinate system, setting up turbulent kinetic energy contours, pressure contours, wall shear contours, pressure coefficient contours, as well as media export settings specifically for images and the settings that I've best found and views that are important for your team to look at. So let's get started by importing the CFD-Post module. I say import, but it's really not that complicated. So first off, you'll want to open a workbench instance with your Fluent module. So these will be your the solutions that you've generated for whichever CFD simulation you've just run. You'll notice that they have completed by the fact that there's a check mark there. You may have already done a analysis on the results that you've gathered, but in this case, CFD-Post is very useful for actually visualizing what's going on in the car and getting qualitative results. You can also get quantitative results from CFD-Post, but this is great for actually visualizing what's going on. So first up, you'll want to get the results module. Notice how it says post in the image. That alludes to the fact that this uses CFD-Post to generate all your media. So you want to drag that right beside your Fluent module, and then drag the solution component of Fluent into the results component. From there, you'll see that you have a results component that you can open. Double click this and it should open CFD-Post. It may take a little bit of time due to the fact that it has to load the mesh. As you develop CFD-Post processing entities, and as your post-processing file becomes more complicated, it will take longer and longer to open CFD-Post. So just be aware of that and no need to worry if it does take a while to open. So double click this and you'll notice it'll start to open in the bottom right. Alright, so CFD-Post has loaded and this is what you should see. On the left hand menu is your CFD-Post kind of a component tree. I'm going to say component and entities a lot, but they may not actually be the real names for all these things, so bear that in mind. But this tree using all your components will have the mesh entities in it. So take note of the fact that you'll have your car, your inlet, your outlet, your road, and your walls in it. CFD-Post is all about generating the results related to the car's performance. So in this case, it will be most helpful to click the checkbox right beside car, and you'll notice that the car appears on our view now. You also have the option of turning off the wireframe if this box kind of annoys you. I find it really helpful just to get a reference point where I'm looking in the space. But if you choose, if you believe that it may not be helpful for you and it kind of annoys you and gets in the way of your pictures or whatever, you can always disable it just by clicking that, and then you'll view the car in free space. Take note of the fact that your coordinate system is very important for how you will use CFD-Post. A lot of the components in this tutorial don't really use things like planes and other locations that involve placing them in the 3D space. But if you have to insert vector planes or vector streamlines at a certain location, then your coordinate frame will be very, very important. So quickly going over some basic camera controls. If you click and drag your mouse, that's a basic rotation. You've probably seen that in many other softwares. A thing that is really nice about CFD-Post is that if you click on an entity in the viewing plane, then it will rotate about that point. So I've clicked just behind the canopy on this arrow body, and now I'm able to rotate about that canopy. If you press Control and left click, you will be able to rotate the camera view. Scroll is just to zoom in and out. And yeah, it's pretty straightforward and very intuitive once you've got the hang of it. A lot better than Fluent, that's for sure. All right, So now that we have our camera controls down, back to the coordinate system for a quick second. It'll be really important, like I said, to get an understanding of where your car is in 3D space and how things move with respect to the coordinate system. So very clearly we can see that the car is in this direction, so left will be forwards. We can see just by the coordinate frame that the x direction is the longitudinal direction of the car. The y direction, positive and negative y, will be the left and right sides of the car respectively, and the z component will be the height of the car, I guess you could say. Yeah. So that just goes over the coordinate frame. Let's now get into generating contours. So we can first get started by generating a turbulent kinetic energy plot contour. This is really helpful for visualizing where the airflow over the car transitions from laminar to turbulent flow. So you'll want to start off by moving your mouse to the top left. You'll notice this icon. This is the contour icon. So click it. You can name your contour whatever you want. I like to have descriptive names, so I'll name mine TKE contour for turbulent kinetic energy contour. And you'll get a settings panel in the bottom left. Domains refers to some things that are irrelevant for the time being. Locations, because a contour is a surface visualization, the location is something that will refer to either a plane or a 3D surface and something like that. So the car is our 3D surface, and we want to see what the TKE contour looks like on the car. So in terms of variables, you'll click it, the drop-down menu, and you have a ton of different variables. You'll notice that the TKE variable is 2 below pressure. When I'm going through this really fast, I'll just start off at pressure and just go down with 2 arrow clicks and press enter. So it can really help speed up your process. And yeah, so range, you want that to be global. Number of contours, this will change the number of colors that will appear on your contour. The more contours you have, the more detailed the contour will be, as in it will show more ranges, more color points, so more data points on the contour. If your computer can handle it, then more contours is preferable. If you really want to simplify the contour, then you can try messing around with a different number of contours. I usually select 5,000 contours just to kind of make sure that I'm getting a full range of data. You'll want to click the plus button right where it says Advanced Properties and scroll down. The variable location, this is a surface, so you want it to be a face. Your color scale for the TKE plot is very, very important. You want to select a logarithmic, or else the data will not appear as it's designed to. Sorry, not as it's designed to, as it should. If you select linear, then your data will simply look kind of unimportant. It'll look like the same color and won't really be very helpful. So a logarithmic color scale is very important. The color map you can leave as rainbow. I find that rainbow 6 can be a little bit helpful sometimes if you have a particularly wide range of colors. But rainbow is fine, and you can play around with each of these different color scales as you please. So next you'll want to go to render. This has a number of different options for how the contour will display on the screen, and consequently how it will look and when you export your images afterwards. There's only one setting that we want to change here, which is showing contour lines. The contour lines is something that could be helpful, could not be helpful, but in my opinion, I think it doesn't look very good. It kind of interferes with how the contours look, especially when you have 5,000 contour lines. So we're going to disable that today. That is all in the contour settings for the TKE contour. You can click apply. It'll take a moment to load, and we'll get back to when it loads. All right, we are back, and we can see that the TKE contour has loaded. So the TKE contour is very useful in visualizing the transition from laminar flow to turbulent flow along the length of the car. You can see here that the bluish hue is the laminar airflow due to the absence of turbulent kinetic energy. As the flow turns from blue to green over the surface of the car, you'll see towards the front of the car, that is, just before the canopy. This means that the flow transitions to turbulent airflow at that point. So we can see that the flow is mostly laminar up to the roughly just before the canopy for the car, and we can also see the transition from laminar to turbulent airflow over the canopy. It transitions pretty far back, so that's a very good sign. More detailed analysis will be done by other members of your team, so your job right here is just to get the data to them and make sure they can see it. All right, so the next contour we want to plot will be the pressure contour. We pretty much did it by generating the TKE contour earlier, but we have to make a separate contour for that. So first things first, we actually want to disable the checkbox beside the TKE contour, and what this will do is it will hide the contour from our view so that we don't have two contours overlaying on top of each other and possibly skewing up the data by overlapping. So what we'll do next is then we will click the contour button, type in our name, pressure contour, click OK. The variable pressure is already selected, that's the one we want. The range can be global again, and make sure that the location is car. The number of contours we want to apply will again be 5,000. We want to ensure that the variable location is face. The color scale can be linear this time, it doesn't need to be logarithmic. And going back to our render view, we want to disable show contour lines. Once we click that, we'll hit apply. It should take a couple seconds to load. The time with which it takes to render the contours of the car will really depend on how powerful your computer is, but in our case it maybe took like 10-20 seconds. Well, regardless, we have here the pressure contour. Again, this sort of data is best left to be interpreted by maybe your senior members, but that is how we would go about it. Pretty simple. All right, next up, we want to do something a little bit more complex here. We're going to do a pressure coefficient contour. So this requires us to do something a bit different, as the variable for the pressure coefficient isn't natively available in CFD-Post. So what we would do is what I would do is I would have to input an expression, a custom expression, and a custom variable, and that would then allow us to select it. So first things first, you have to click the button in the top that says expression. Let's name this expression CP expression for coefficient pressure. All right, so you'll get a big blank white box. What you want to do here is you want to type in a formula in CFD-Post's language. This can be found online. What this equation is just the equation for the pressure coefficient based on the values at the inlet. So what you do is you type bracket pressure minus reference pressure bracket divided by 0.5 times area AVE density at inlet times area AVE velocity at inlet squared. So this can be explained if you want an explanation for this, you can just look up the ANSYS documents for the coding language and stuff. But yeah, I won't go into this too much. All right, so click apply, and then you'll see that the CP expression appears on your list of expressions. Next, what you'd like to do is you will need to enter a new variable. So in this case, we just made a CP expression. So let's maintain our naming scheme and name this CP var. The method will be expression. It is a scalar quantity. Its expression will be, here we are, CP expression. Calculate global range and click apply. All right, that took a couple seconds. We can now go back to our main entity menu. We can deselect pressure contour and get the base car again. And we can create a new contour. Let's call this CP contour. Again, location will be car. The variable, now you can select CP var. the range will be global, the number of contours 5,000, and as usual select face, the color scale can be linear, and disable show contour lines. Click apply and it'll show up. All right, our CP contour has generated, and again, it's probably best to leave the interpretation up to your senior team members. All right, next, we are going to deselect our CP contour again. The pressure contour was enabled. I was doing some stuff in the background, but yeah, disable both, because next we're going to do something a little bit different. We're going to click Streamline, because we are going to make our wall wall shear contours. So if you don't know what wall shear is, I recommend that you do some reading on wall shear Streamline. Sorry, there we go. Yeah, sometimes CFD-Post will give you that error, and you will need to make sure that you'll have to rename your variables so it doesn't conflict with something already built into CFD-Post. If you don't know what wall shear is, it's best to do some reading on some arrow theory beforehand. But that is what we're going to do today. So a wall shear streamline, you will, after creating the streamline, you will open up the Streamline editing menu. A wall shear streamline is a surface streamline. It is not something that exists in free space. It exists only along the surface of bodies. So the type of streamline we want is a surface streamline, not a 3D streamline. It is important to select the car as your surface. Unlike the contours, this will not already be selected for you. You can start from equally spaced samples. I like to have 500 points, as I find that to be a good balance between being able to see the car and see the streamlines. If you want to have more streamlines and have maybe more details, you can choose a higher number, but just know that it tends to crowd all the streamlines together, so I find that it's not very easy to read. You want the variable to be wall shear, again, because there's no velocity of the air that low to the car. Again, read some aero theory textbooks before, maybe if you want to learn more about wall shear. Direction, forward and backward, already selected for us. The color, it is preferred by Blue Sky at this time for us to use a constant color, as we don't find the wall shear data to be especially useful at the moment for our design goals. So what I just did there was I changed the mode for the color from a variable, from useplot variable to constant, because I want the variable, the streamlines, to be of constant color. Click the three dots and go to select your colors. You can use the entire color spectrum and choose whatever color you want. I tend to find that the blue preset is good enough for me, and you can just click OK and select that. The symbol, I usually bring down the thickness of the line to 1, just again to make sure that they aren't overlapping too much, and then it's still decently visible. You don't really need to change anything else in these settings. Again, so this will take a while to generate, so just click apply and you'll be good. All right, the wall shear streamlines have generated. You can see them along the surface of the car. You can probably guess what they're doing at this point. It's not as complicated to interpret as the other contour plots, but again, probably best left to be interpreted by your senior team members. All right, so now that we're done all the streamlines and contours that we usually use in Blue Sky, it's important that we need to export the media in order to be able to get everyone able to view it, because CFD-Post Viewer is nice, but it's not as nice as the post-processing images that can come out of it. So we export our media as images. CFD-Post gives you the option to do animations, but they're not particularly useful, as the static analyses are preferable. So in our case, it is important that we get images of all the important parts of the car. This will mean taking pictures of the left side of the car, the right side of the car, the front of the car, the rear of the car, the top of the car, the bottom of the car, as well as some isometric views. So this would be the top right, the top left, the bottom left, and the bottom right. So in total, that's about 10 different views that we have to make. So I will start this off by deselecting the wall shear streamline just to get a clean view again. And this is where knowing the coordinate systems becomes really important, just so you can quickly pan around and select preset locations. I'm going to select the -y arrow in CFD-Post and the coordinate arrows in the bottom, and that will bring me to the left side of the car. Click and hold the right mouse button to select an area that you want to view of the car. I'm going to zoom in a bit more because I generally know how I want the car to look in the picture. So I usually go just a bit beyond the edges, just due to the scale that I'm using. Next, you can click Control P, and that will bring up the Save Picture dialog. Take note that the file that it is saved, that the folder that it is saved to will usually be one of the obscure workbench folders. So I recommend, if you want this to be easily accessible, that you organize where you're going to be putting these things. So I'm going to put these in the same folder as my general folder for this case. I'll make a media files folder for it. And I'm going to name this, I'm going to start off by generating the CP contour. So I'm going to name this CP contour 01 for the first image, left side .png. All right, so my naming convention is typically the type of plot that I had, just a number in the number of images, so I know how many images I'm supposed to have and which one it is in the set. And because other people will be viewing the image, I want them to be able to quickly know which side of the car they'll be looking at without having to look at the preview. I rate the view that I had. So in this case, it was the left side. So click Save to select this as the location. Oh shoot, one thing we forgot to do actually was to actually select the contour that we want. So in this case, we're going to start out with the CP contour and press Control P again. That did not save the location, so unfortunately we're just going to have to write that again. CP contour 01 left side .png. All right. The format will save as a PNG. I prefer not to have these as raster images, so I prefer to have lossless files, not lossy. Lossy files, not lossless. And I don't want to have them compressed either. So no JPEG, no raster images, just a PNG is fine. Deselect use screen size. I have found that I need to capture a lot of details in these images, so it's optimal that I increase the resolution. In this case, I found that the image size that is preferable for me is a width of 8,000 pixels and a height of 4,000 pixels. If you decrease this resolution, then it'll also decrease the size of the file that's created. So do note that higher resolutions, you kind of have an decreasing returns with higher and higher resolutions, and as well as higher file sizes as a result. So don't mess around with the tolerance, just these settings is fine. We can save, and we should be good to go. It'll take a minute, it'll save graphics data to the file, and then it's done, all right? Then we can move on. I will usually take a picture of all the data from this view so that the view is consistent through all of them, as opposed to moving my camera around and finishing all the views for one contour and then moving on to the next. So that way I don't have to move the camera around. CFD-Post does have options to save camera locations, but they're not very easy to access, and you can only do that by through a script. So I don't really have the time to do that. So instead I'll just keep the camera where it is. All right, next we're going to do the pressure contour. Press Control P again. Just to make myself easier, to make my life easier for myself, I'll do all the contours first. So I only have to change the pressure contour. Everything else can be left the same as a result of my naming scheme that I've chosen. If you care to choose a different naming scheme, it's up to you. I just choose this because that's what I prefer. All right, so pressure contour is 01 left side.png and save. right? I'm going to skip ahead and finish off these ones for the left and the right sides. Taking a picture of the right side is as simple as, instead of choosing the negative y direction, just choose the positive y direction and repeat the process on the right side. So I will skip ahead to when I've finished all these left and right side images. All right, so now I'm on the right side of the car and I've just finished taking pictures of all the images for this side. At this point, we're going to try and do the ones for the front and the back. So I'll just do the front as a demonstration and the rear can be left to you guys as an exercise. So here I'll actually start over on that view again. Starting from this view again, what you want to do, again, be really aware of the coordinate system with the car. At this point, you'd want to click the negative X arrow. It'll rotate the view like this. You can simply press Control and the scroll wheel. Sorry, don't press the scroll wheel. Use the scroll wheel to rotate the view and make it perfectly square. Again, click and hold the right mouse button to draw a rectangle where it will magnify onto the screen. You can zoom in a couple times, adjust the view. If you notice that the car is cut off or too big or too small on the viewing plane in your pictures, so you would check your pictures to review how all of them look afterwards. I'd make sure you double check your work. And if you notice that any of this is happening, then you can simply adjust the view. So if the car is too big, then zoom out. If it's too small, then zoom in. And if it's cut off, then you can move out, pan around, which you would do by clicking Control and the middle mouse button. You can see the mouse turns into a translation icon as opposed to a rotation icon. So at this point, we are now at the front of the car. We can see that part of it is illuminated. Press Control P. Make sure you select your CP contour again. That happens a lot. Change your naming convention as usual. So now we're going back to CP contour 03 because I just finished the left side and the right side. And you want to change that to front. Okay, so CP contour 03 front. Save it. And you should be good to go. All right, I'm going to continue through the rest of these. The rear is pretty simple. It's the same process, except instead of clicking negative X, you'd click positive X. You'll just have to drag around and view that arrow. And I'll come back when I'm ready to do the top and the bottom. All right, at this point, I've finished my exports for the front and the rear. I'd like to now take pictures of the top. So again, be aware of your coordinate system. Know that the top will be positive Z. So click the positive Z arrow. You can see you have the top view. Use the right click, use your mouse right button again to click and drag on the area that you'd like to focus in on. So that'll be the car. Bring it into view. You can zoom in a couple times because an 8,000 width is pretty big, so it'll should be quite comfy. All right, there we go. That's roughly where I'd want it to be. Then you will make sure you have your CP contour selected and press Control P and enter in all your usual information. So CP contour, CP contour 05 now, top .png. Perfect. All right, so click Save and wait for it to go, and you'll be ready to go. Again, I'll go through my pressure, TKE, and wall shear streamline images for the top and the bottom. For the bottom, instead of clicking positive Z, you'll click negative Z and do the same process over again. So I'll come back when I'm ready to do the isometric views. So that'll be the diagonal views. All right, so at this point we have finished taking pictures of the top and the bottom. So I'm going to enable CP contour again, and we'd like to start on our isometric views. So what an isometric view is, it's kind of like a diagonal view taken from not a view that's not directly in line with one of the axes. Yeah. So I'd like to start by taking a top right isometric view. So what I'm going to do is I'm going to rotate the car a really handy feature of CFD-Post is that you can left click on any surface to rotate about that point. So when I'm making an isometric view, I usually like to rotate about the point right behind the canopy because it's not too close to the front and not close to the back. It's around it's a good central point for the car. So I'm going to rotate the car around. You can choose a different center of rotation if you'd like, whichever works best for you. So what I'm going to do here is I'm going to try and get a good view of the top and the side of the car. So I'm going to do a mix of panning, rotations, and yeah, that's pretty much it. So it takes a little bit of working around until you can get somewhat of a good view. What this view is particularly good for is the wall shear streamlines. I'll enable them for a second. When you review your pics, you might see that there are some streamlines that cross over from the top to the side of the car. If you have any of the views that just are purely on the axes, you won't be able to see this transition over the side of the car, which is what these isometric views are really good for. So again, work through your CP contour views, and we will, I'll actually go through them because it's pretty important to be able to understand how you can transition from one to the next. So I'll just fast forward here. All right, so we've just finished our wall shear. Let's enable CP contour again, and let's rotate to the other side. So what I'm going to do is I'm going to use the default rotation by clicking and dragging my mouse to pan over to roughly this location. Then I will use my planar rotation tool. So that'll be control mouse. You can click it and you'll rotate just about that point like that. I'm going to zoom out a bit because this is a bit far from our liking. I'm going to try, what I want here is I want to get more of the side of the car exposed. So I'm going to rotate a little bit, bring the car a bit farther down. These views can get kind of tricky. And then you can see that this view is kind of adequate, but a lot of the car is still darkened. So a really handy trick at this point is to adjust the lighting for the car. So if you press and hold Control and right click, you can move the light source around. So ideally you want to have the top and the bottom, sorry, the top and the left half of the car visible. So I'm just going to move the lighting around and see which, when both positions will become visible without creating too much glare. You can see that if I move the light source around, it will create glare, particularly around certain areas of the car where you don't. So yeah, just it'll create some glare. So you want to try and adjust the light source so that it will maximize the visibility of your data while also minimizing the amount of glare on the car. So let's just move the light source over here, and we can go ahead and start taking images for this side of the car again. So CP contour. My naming scheme is the same as usual. CP contour 08, top, left. I'll get back to you guys when I'm done. Alright, so I've finished my images for the top left of the car. What I'd like to do now is I'd like to take the isometric views for the bottom of the car. So I'd like to stick to the left side just because it's easier than shifting my camera all the way to the right side and then back to the left again. So I'll rotate the car, bring it, shift it this way, rotate it down, rotate it a bit that way. This part, it's hard to be exact when you come to your isometric views just because they're not directly on any axis by definition. So you can get a bit creative with your angles here and just decide which look best. So a good example of having to adjust the lighting would be in this example where I just moved my lighting around to light up the bottom and the left hand a bit better. But you'll notice that I created a large bit of glare around the trailing edge. So I want to try and move my light around so I can minimize that. It actually looks like this angle might be the best of the rest, because you don't want to create too much glare on any other surface, and you also want to make sure that everything is evenly lit. So if I moved it above, then the glare would move to this part of the trailing edge, but the bottom would be significantly darker than the side. And if I moved it down here, then there's a lot of glare around the middle now, and there's still a lot of glare around the trailing edge. So actually having it in that original position, kind of around here, would be good. Yeah, around there. Around there. All right, at this point, let's start taking our pictures at the bottom. All right, we're done our bottom left. Last one now, let's move around to our bottom right. So rotate the image down again. There's no particular order that it comes to when you're trying to get these views. It just comes to how you're going to do it. You might notice that there's a little bit of an anomaly down here that might indicate an error in meshing or an error in the sim. So it might be best to consult with some expert advice to verify whether results for your sim are accurate in that case. In this case, the job here is just to get the post-processing done. So we will alert anyone of any anomalies like that. So make sure to keep your eye out when doing this kind of task. So again, let's bring the lighting up to par with what we'd like. Just want to make the evenness good. All right, that's done. Looks like our lighting is good. A little bit of glare on the trailing edge, but the front and the bottom side and the belly pan look pretty good. So let's take our images again, and we should be done. All right, so at this point we've exported all our contour and streamline images, and we'd like to create a different kind of data plot. So up until this point, we've been generating 3D or surface data. So our contours were all 3D. I mean, they were on the surface, and our streamlines were exclusively on the surface. So the CP contour was really useful for visualizing around the car, but another useful kind of CP plot is called a 2D CP plot, where we will create a line that goes along the center line of the car, up along the canopy, following the trailing edge, down the bottom of the car, and up back around to the nose. So if our goal is to create a line here from which we will sample points, and along those points we will get the CP data at those points. And that CP data really helps us find adverse pressure gradient regions where we can maybe experience pressure drag or extra skin friction at those areas. So we can start off here by being aware of our reference frame, so we can know that if we're trying to sample a line along the center line of the car, then it's probably going to be of constant coordinate in one. Sorry, it's probably going to be of one constant coordinate, and that will be the y equals 0 coordinate. We would also need to know that if we were trying to sample a location along that line, it's probably best to know that the location is going to be in the x direction, not so much the z direction, as a unique x coordinate will only give us one of two possible points, one region above or below the car. So let's start off by clicking the location button and then clicking the isosurface button. This will generate a plane. So we're going to generate a plane in the y equals 0 location. So y0 plane is what I'm going to call it. And you can click OK. Domains, it's going to be all domains. The variable will be of constant y, so y equals 0. The color can stay the same and everything else is good to go. The domain, make sure that it is unspecified. So this unspecified is part of the fluent domains. And you can click apply. It should be good to go. All right, so you can see our plane is here. It can be plainly seen. Haha. It can be clearly seen that it intersects down the center line of the car. Yeah, so if we tried to sample CP info from this plane, then it would sample points around the whole plane. It wouldn't sample points just along the edge of the car. So what we want to do here is we want to create a line that intersects the y equals 0 plane and the surface of the car at the same time. And that would give us a perfect silhouette right down the center line of the car. So you can uncheck the y equals 0 plane and then click location and then click polyline. And let's name this polyline the centerline polyline. All right. Domains, I'm just going to double check our reference here. Make sure the domains are all domains. Always be sure to go back to your reference material if you're not sure. The method here will be a boundary intersection. The boundary list, the first one will be the car, and the second one will be the y equals 0 plane. The color doesn't matter here, but just to be descriptive, we're going to choose the CP var variable that we created earlier. The range can be global, and you can just click apply. All right, there we go. You can see we made a line straight down the center line of the car. You can see that they have there are pressure. There's a high pressure coefficient near the nose of the car and a high pressure coefficient at the leading edge of the canopy. It's a lot easier to read this data off the plot, but you can see the similar data as well in the 3D CP surface contour that we created earlier. Regardless, we're now going to move on and create the plot from the points that'll be sampled along this line. So first things first, move your mouse up to the top of the screen and click chart. You can name this chart CP chart. I actually want this chart to be sampled along, well, there are two ways to describe a chart that measures the pressure coefficient along this line. So you can describe it by having the point be attributed to an x location, so a distance, an x distance from the nose of the car, so 1 meter or 2 meter or 3 meters or 4 meters and so on away. At any given x coordinate, you can be either one of two locations. You can be either above or below the car. Or your other option is to represent the plot by representing each pressure coefficient point as a function of the length of the line. So let's say that if your given line starts at the nose, then maybe 1 meter along the line will be here, and 2 meters will be here, and so on and so forth, and you'll always have a unique location for the line. A downside to choosing this option is that the line does not necessarily start in the same place every time, so you'll have to look up and compare the two different charts to understand where the line has started in your instance. But yeah, that should be a good way to separate the upper and lower pressure coefficient charts as well if you need to do that. Regardless, let's go back and create our chart again. Sorry, just click cancel there. So if you already had your chart open, you don't have to do that. But let's start off by making the x coordinate CP chart. So CP versus x coord chart. All right, so our type will be an XY line, display title. Let's name this CP versus X position, or X coordinate actually. The data series here will be centerline polyline. Sorry, the location will be the centerline polyline. Of the X axis, we are sampling points and relating them to the X coordinate. So you want to scroll down and click X. You can determine ranges automatically. If ever you have anomalous data and you realize that one point or so may be off with your mesh and the rest of the mesh you've decided is still accurate, then you can adjust the ranges if necessary. But for the most part, sorry, this would actually apply to your CP var, your y-axis variable. But for the most part, stick to determining ranges automatically. Sorry, yeah, so your y-axis variable would be CP var. You will determine ranges automatically, and you don't really have to press anything else. Click apply, and here is our plot. So you can clearly see that we have two lines. They will have two sampled locations for each x coordinate, like I said before, and you can relate the 3D image of the CP contour to these values on the plot. And by isolating those regions, I could probably guess that the high CP value we saw earlier at the nose and at the start of the canopy would probably give me an idea that this line is the part that follows the top of the arrow body, and this one is the one that follows the bottom of the arrow body. So at this point, it's a good idea to also export an image of this. So if you press Control P again and navigate to the right directory, so I'm going to go to my media files directory that I had earlier. I'm going to name this CP versus X coordinate.png, and I'm going to make this a 2000 by 2000 chart. Click OK, and it'll save a quick image of that. What you can also do, which is something I really recommend, is you can export the data series. So go back to your details for your chart, click on data series, and then click export, and it gives you the option to export the points, the x coordinate points, and the CP values accordingly as a CSV. So I'm going to go back into my media files folder, and I'm going to name this CP versus X coordinate.csv and save. I really recommend doing that just so you can have numerical results if really needed. It'll help your design team in quantifying where some of these values are occurring. Yeah, so this would be the X coordinate chart. Another chart you can do would also be a chart versus the line length, as I discussed earlier. So let's do that. Let's make a new chart by clicking the chart button again. So let's name this CP versus poly centerline poly. Let's name this center poly length. Okay. Same as before, XY line, that's the type. Display the title. C versus length of the center line. Line polyline. The data series will again be the centerline polyline. X-axis this time, instead of the X value, will be the curve length on the centerline polyline. Determine ranges automatically as usual. The Y-axis will be CP var again. Click apply. And this is the other kind of chart. So as you can see, this chart goes up to 10, which means that is or just past 10, which means that the length of the centerline polyline is approximately that distance. It's really difficult to get an exact length of the polyline just because these points are sampled along it and not necessarily at the 0 and maximum point. In addition to that, the polyline doesn't necessarily start at the nose of the car or the tail of the car. So if I compare it to my X-chord chart, let's see, there should be 2 points where the line goes to 1, and there should be 1 point only where it goes just above 0.6. So if I'm looking, this would probably be the point where the line was at the nose of the car, and this is the region where it probably hit the canopy. So again, comparing those two charts, something like that is how you would analyze this and figure out where this line started. So given that this is in the middle, I'm going to guess that this probably started at the tail. You can do a more rigorous analysis if you want, but it's a pretty rudimentary way to do this. So again, export the data. You can just edit the name here. CP versus length of centerline polyline. 2000 by 2000 again. Click OK. And again, export the data as CP versus length of centerline polyline.csv. All right, and that's all. At this point, it'd be a good idea to review your images and make sure you have all the views that were required of you. It would also be a good idea to go through your charts and make sure they look good as well. And if you want, it would also be really useful to go through the CSVs for the CP plots and make sure that the data there looks good as well. And that's it. Thanks for watching and good luck with all your work. Cheers.